Hi, my name is Erica Carlson. I'm a theoretical physicist here at the Purdue Quantum Science and Engineering Institute. And we are delighted to have visiting with us this week Dr. Paul Canfield. Paul is a senior scientist at the Ames National Laboratory. He is a distinguished professor of physics at Iowa State University. He's the winner of numerous awards. I won't bore you with all of them, but just to mention a couple of your recent awards, he's the winner of the Humboldt Research Award and the McGrady Award for Materials Research. And perhaps your most important accomplishment prior to those awards is that you got your physics PhD from UCLA. Is that right?
Yes.
As did I. Go Bruins.
Ooh,
Come on,
I
don't leave me hanging,
cultivated
man.
ignorance of all sports.
So
my greatest achievement before that time was getting a picture of one of my pastries published in the journal Nature.
Okay, that is impressive. I'll
Yes,
have to
okay,
ask you
right.
about that story. Maybe that's for another story time. So one of the things I want to ask you about is to tell us about why scientists and engineers are so excited about quantum materials today.
Well, I would argue that it's not just quantum material. Historically, if you think of the epochs of history, you have the Stone Age, the Iron Age, the Bronze Age. We've been in the age either of silicon up until maybe a couple decades ago. I would argue we're in the age of new materials, novel materials. There are just hundreds of new materials that are being discovered endlessly, and these are the materials that so many scientists are trying to design, develop, master, understand. So it's not just quantum materials, or quantum's part of it, but it's a drive to create the materials that will solve humanity's problems.
All of humanity's problems. Or
Oh God,
maybe just
everyone
sort of a
except
subset maybe?
No, we're not going to improve the time it takes for pizza to be delivered.
Okay.
That's unsolvable, but beyond that, we're good.
Okay, fantastic.
All right.
So what's something, or what motivates you to go into the lab and do science?
Oh God. As an experimentalist, I think either I would be an experimentalist or a compulsive gambler, because
Okay, so just explain experimentalist. That means that Paul goes into a laboratory and he measures things.
right.
Is that fair?
And yeah,
Okay.
but you skipped a step.
Okay.
Okay, so my lab works on sort of a closed loop of think, make, measure, think. Okay.
Fantastic.
So the compulsive optimism is we try to discover new materials, new ground states, new states of matter.
Mm-hmm.
And we will go into the lab in a good morning and take new growths out of furnaces. And when we do
Which
it,
means crystals, right? Is that what new growth means in your your lab?
inshallah. You know, if
You don't even know what you just said.
it's a beautiful Arabic phrase, roughly translated, if God wills it.
Fantastic.
So, inshallah. When you go in and you take a material that's glowing red hot, drop it into a centrifuge, spin it, and then let it cool and open it up, it's nature's Easter egg. Okay?
You're talking about when you have created a new material, something
Well,
that no one has made
hopefully
before.
when we're creating
Right,
a new material.
right.
So you then get to open up this little Russian doll of nested silica and alumina crucibles, and then inside sometimes you'll see this shiny little object, and the object can be a single crystal of something that's never existed in the history of humanity. And there is this exquisite, just Zen moment of proximity to nature. There's also a magpie-like moment of, ooh, it's shiny, I want to put it in my nest.
Sure.
But then you get the pleasure of starting to interrogate nature. Because when you make a material and then make a measurement on it, you're asking nature a question. Okay?
Yes.
Or you're asking the material a question. You're saying, are you what I wanted to make? No, I'm new. What are you? I'm an insulator. What type of
Fantastic.
insulator?
And each
so
of these
forth
questions,
and so
by
on.
the way, involves a
measurement.
an experiment.
Yeah, exactly.
It involves time, it involves money, and it involves effort, and it involves
Ooh.
expertise. But
Sometimes you can do it quickly.
okay.
Sometimes
So
you can.
what's the quickest you've gone from opening
24-hour
up the
cycle.
Easter egg
24-hour
to
cycle.
I know what I have?
Oh, sometimes I know what I have is almost the disappointing answer.
I
but,
see.
But no. But
No, you're right, because the most exciting thing is when Paul opens it up and he doesn't know what he has,
Oh.
and then he publishes really cool data.
after I know what I have.
And then when it comes to the rest of the community. And we also look at it and go,
Right.
that is something entirely new we've never
Right.
seen before. That's where really exciting stuff happens.
So you can cycle this sometimes in 24 hours. It's really neat. You can take something from glowing red hot in the morning, and by lunch, it can be within a gnat's wing of absolute zero. And then as you warm it up, you can see that it has a phase transition.
Yeah.
And in the evening, you can put another growth in. Now that's sprinting.
That is.
And
That's
sometimes
fun.
you sprint. Okay. Sometimes it's more leisurely. But you were saying what motivates me. Part of it is the same muse that motivates you if you enjoy cooking. Many of the students I have, I'll ask them when they interview, do you like to cook? Because I love to cook.
Are the requirements for your lab, or are you just trying to get to know people?
Well, no. Look, there are a couple things. As experimentalists, I want to know if they have hands.
Yeah,
So there was this one woman who came in, and as an undergraduate, she took apart old Mustang engines and put them together. I wanted her in my lab. She had hands.
Yeah.
Okay. If you enjoy cooking, it's also a similar muse, because in the same way that if you want to try a new recipe and invite friends over to share it, and you're not too sensitive of a cook, so you can then after the meal do a post-mortem. Do you think it was too spicy? Do you think it was too greasy? Did you like the nutmeg and the white sauce? I thought about the flavor out. In the same way, if you discover a new material, it's like having a protracted dinner party, because you share it with your friends. You go, oh, wasn't that great for scattering? Or, my God, I think it's a new type of transition here, and I think the pinning is fantastic, and maybe we'll make a patent.
That's a great metaphor for what it's like
Well,
going to a
it's
scientific
like
conference. It's very exciting. It's like we have new ideas, we get very excited about things, we're talking with our friends about science. And so, look, one of the things I'd also like to ask you about is what's going on right now in your research group that your group is most excited about?
Well, we have a lot of Latin Americans right now, so we're exploring different types of paellas. And, paella is as well as Indian, so it's like a pilau. So a pilau and a paella are related to each other in sort of a continuum of cooking. So that's one of the things we're really excited about.
Okay, all right, and then science-wise.
Oh, science! Oh, good Lord.
Science-wise that you're most excited about right now?
Yes, a multitude of things. So, really,
pick your favorite.
The neat thing, well, let me do a plug for condensed matter physics.
Okay, great.
Okay, condensed matter physics is the study of the solid state, often of materials that derive their properties from their crystalline structure. That's not everything, but many of it. Okay, it can cover a wide range. So on the applied side, we're trying to find new ferromagnets that are either reduced in rare earths or not containing any rare earths. And the reason we're trying to remove rare earths is they're expensive to produce in high purity form, and they're environmentally damaging. Okay. On the other extreme, we're trying to answer basic questions of how do new states arise? How do you use spontaneous symmetry breakings or emergent properties? So you can take a metal at low temperatures and apply pressure, and it's a metal, it's a boring metal, it's becoming a little more magnetic in its fluctuations, and all of a sudden there's the birth of magnetism. Okay, that's called a quantum critical point. And sometimes during this period of fluctuations of magnetism, new states will occur, superconductors, stuff like that. So one of the things we're trying to do is to find weakly magnetic materials that we can perturb. We can, if you want an analogy, remember, bullying is bad. Do not do this at home. But you can take a material and you can bully it. You can call it mean names. You can do horrible things to it. And you can make it shrink and feel small and whatever. But right before it sort of disappears, it will go, no, I must be something else. And, it will become a superconductor. It will become some other type of material. And this is very poorly understood, but it's where a lot of the interesting properties are. This is where we think room temperature superconductivity
right, so if we can kind of summarize, maybe one of the things that you're excited about those kind of materials where you get very interesting things going on near the transition is because they become rather susceptible to our control. Is that accurate to say? Because the susceptibilities go high? Yeah,
no, that's a nice analogy. The last analogy I used was flawed and not so good. Let me try to do a better one, okay? Classic Greek-Roman mythology have the sense of a phoenix.
Yeah.
A magical bird that dies and then is reborn from its ashes. Okay? A lot of these materials are like that. You'll have one state that dies in the frigid cold of absolute zero,
Yeah.
but then something else emerges because we have this concept of, entropy.
Yeah.
Okay? And something has to be built out of that. Okay? So it's as you're squeezing one state away, something else pops up. It's sort of like trying to
Yeah.
squeeze a water balloon, and all of a sudden, bloop, something else pops out that way.
Exactly.
Yeah, exactly.
Right. So we're kind of running out of time,
Oh,
but
dear.
it's really fun to talk with you about science. So I look forward to many more great conversations with you this week, and we're glad you can be visiting us at the Quantum Science and Engineering Institute.
Well, it's a pleasure to be here, and it's a lovely town. I was happy to come visit.
All right. Thanks, Paul.
Press the button.